Hey everybody, Jungjin here for our second video in the wind tunnel experiment series, and in this video I'll be talking more about the quality of the flow in a wind tunnel. So in the first video, we classified wind tunnels into two main categories, open and closed circuit. Now, I did mention that there are other ways to categorize wind tunnels, like the operating speed, test section size, and purpose. So if you want to know more about these other classifications, feel free to let me know. But the distinction between an open circuit and a closed circuit wind tunnel is one of the first things that you want to understand. Alright, so both open and closed circuit wind tunnels have essentially the same function. So why would you want to create a closed circuit tunnel and have the added complexity of corners and significantly higher cost to design and build? Well, if you think about it, an open circuit wind tunnel draws in whatever surrounding air there is in the room, which means you don't really have control over the temperature or the humidity of the air that you're running your experiments with. Or in other words, your experiment results could be noticeably different at different testing times, like morning and afternoon. Whereas in a closed-circuit wind tunnel, there are heat exchangers or active cooling mechanisms to keep the air properties controllable and very consistent. Not just that though, a closed-circuit wind tunnel can give you much more uniform flow because of the additional guiding vanes and flow straighteners, and the actual operating cost would be lower because the fan doesn't need to keep sucking in new air and accelerate it. And it does tend to be a lot more quiet than an open wind tunnel. So closed circuit is starting to sound really good, right? Absolutely. But again, it's very expensive to build, and if you wanted to test some like propulsion systems with an exhaust or use smoke for visualization, the particles would accumulate in the circulating air, so you would have to design some sort of like purging mechanism as well, so more money. But moving on, there's another aspect to consider in terms of flow quality. So you just learned about boundary layers over a flat plate in class, right? Well, the inner walls of the wind tunnel are essentially flat plates, so you could expect a boundary layer to grow along the free stream direction. And you can imagine this can't be good because if your boundary layer is large enough, it could be affecting your test setup. So this is definitely something that we want to measure first before we do any sort of experiments.
Okay, so in this workshop, there are a lot of tools and machines here. Basically, Young Sifu here, hi Sifu, will will help you build basically any equipments or models that you might need for your wind tunnel experiments. What they're doing right now is they're installing a Cobra tube. When that tube can go up and down, it's actuated by this lead screw here, which Sam has built. And yeah, that'll help us get the velocity profile of the entire wind tunnel.
So this Cobra probe is really cool because it measures the free stream velocity in the entire XYZ component, meaning you can check how uniform or turbulent your flow is. And what we're trying to do here is take these measurements along the entire height of the test section using this actuator here. So we got the velocity profile of the test section at a free stream velocity of 20 meters per second, which is what we will be using for our experiments, and the boundary layers are about 20 millimeters thick from both top and bottom surfaces, while the turbulence intensity measured to be around 0.3%. And if you don't really get what that means, it just means that for the scope of our experiments, the flow quality is pretty good. That's it for video 2. Sorry for the long wait. I promise the next videos will come up much faster.